Welcome to The Explainer. Today, we're diving into one of the most powerful tools in machine learning, the random forest. Now I know, it sounds kind of complicated, right? But the idea behind it, it's actually surprisingly simple.
So, let me ask you something. Have you ever relied on just one opinion and totally regretted it? You know, your one friend swears by a restaurant, you go and it's just awful. Or maybe you followed that one hot stock tip and, well, we all know how that can go. It shows you, right? Relying on a single point of view can be a huge gamble.
And here's the fascinating part. Machine learning models, they can fall into the exact same trap. You can have this one supposedly brilliant model that just gets things spectacularly wrong. So what do? Well, instead of trusting just one expert, we builded a whole committee to make the final call.
And that really gets to the heart of what we're talking about today, this whole idea of one single expert versus an entire committee.
Now, this committee idea isn't just a cute analogy. It's a real, powerful technique in machine learning called ensemble methods. And it's pretty much what it sounds like. You get a bunch of models together, an ensemble, and you combine all their predictions. The goal? To get a much more solid, reliable answer than any single one of them could ever give you on its own.
Yeah, this quote from the source material just absolutely nails the philosophy here. The point isn't to find that one perfect genius model. It's all about leveraging the collective wisdom of a diverse group.
Okay, so let's get specific. Take a single decision tree model. It can be super smart, but it's also really unstable. And what I mean by that is, if you just tweak the input data a tiny bit, you can get a completely different model with wildly different answers. They're also notorious for overfitting. That's where they basically just memorize the data you show them, instead of learning the actual patterns. But when you have a whole forest of these trees, well, they start to average out each other's mistakes. It makes the final prediction way more stable and robust.
Okay, so this committee of models sounds great, but how do you actually build it? How do you make sure the members are diverse? It all starts with this really clever technique called bagging, which is the foundation for our entire forest.
Bagging is just a shorter way of saying bootstrap aggregating. The big idea is this. You take your original data set, and from that you create a bunch of new, slightly different training sets. Then you train one model on each of those new sets, and the absolute secret sauce here is something called sampling with replacement. Let's really walk through this, because it's important. Imagine you have a big bag of marbles. That's your original data. You're going to make a new bag of the same size. So you reach in, pull out a marble, note its color, and here's the crucial part. You put it back in the bag. You don't keep it out. Then you pick again. Because you're putting it back, you could totally pick that same marble again, and again. And you just keep doing this until your new bag is full.
And you can see exactly what happens here. Since we're putting those data points back every single time, some of them, like A and C in this picture, might get picked a few times, but then others might not get picked at all, just by random luck. And by doing this, we end up with all these unique data sets to train our committee on. Each one is a little bit different.
Okay, get this. This is a pretty wild stat. When you do this whole sampling with replacement thing, on average, any one of your new data sets will only have about 63.2% of the original unique data points. The rest, they're all duplicates. It's this little mathematical quirk that's absolutely key to making sure our models are different from each other.
All right, so we've got bagging down. That's step one. Now we're going to add one more little twist, and that's what turns this into a proper random forest.
So here's the whole process from 30,000 feet. You start with your big data set at the top that gets broken up into all those unique sample data sets we just talked about. We then build one decision tree for each of those samples. And at the very end, we pull together all the predictions from every single tree to get one superpowered final answer.
Now, this is where the random part of random forest gets really interesting. It's not just about picking random rows of data like we did with bagging. There's a whole second layer of randomness. Every time a tree has to make a decision, what we call a split, it's only allowed to look at a small, random selection of the features. So, why would we do that? Well, it forces each tree to learn in a different way. It prevents one or two really strong features from dominating every single tree, and that creates an even more diverse and ultimately a more powerful committee.
Okay, so we've built this forest. We have all these different trees, each with its own opinion. How in the world do they agree on a final verdict?
It's actually super simple, kind of like a democracy. If you're trying to classify something, say, will this person default on a loan or not, every tree gets a vote.
the final answer is just whatever the majority voted for. Simple. And if you're trying to predict a number, like the price of a house, you just take the average prediction from all the trees in the forest. That's it!
All right, let's take this out of theory and into the real world. The source material has this fantastic example of using a random forest to predict if someone's going to default on a loan.
Now check this out. A standard random forest had a high accuracy of about 98%, which, sounds amazing, right? But here's the problem. Its recall, which is how good it is at actually finding the people who default, was only 35%. For a bank, that's pretty useless. So the team tried something clever. They used class weights. It's basically telling the model, hey, finding a defaulter is way more important than correctly identifying a non-defaulter. And look at the result. The overall accuracy only dropped a tiny bit, but the recall, its ability to catch those risky loans, doubled to 70%. That's a huge improvement.
And this is the big takeaway right here. The best model isn't always the one with the highest accuracy number on a spreadsheet. By making sure the model was focused on the real business problem, which was catching those super rare but really expensive defaults, we ended up with a tool that was way, way more useful.
So there you have it. You take a bunch of simple models, you inject 2 different kinds of randomness, and you end up with a random forest, a seriously robust and powerful predictive tool. We've seen how this wisdom of the crowd approach can be tuned to solve real business problems. It really makes you think, doesn't it? If a whole forest of models can be this powerful, what kind of problems could you solve with it?